Okay, so what we're going to be looking at here is we are going to be looking at how to do each of the problems on the review for the first test. If you have any other questions about any of these as far as how you do them, please just get a hold of me as soon as you can. But this should show you how to do all of the different problems. So on the first couple of, the first 9 problems actually, what we're being asked to do is we're being asked to evaluate a limit algebraically. Now remember, anytime you evaluate a limit algebraically, what you're really doing is you're taking the x value that we are approaching, and the first thing we always do is we just plug it in. So everywhere we see an x. So in this case, I get negative 2 times negative 2 to the third minus 2 times negative 2 squared plus 1. So here I get negative 8 minus 8 plus 1. That gives me negative 15. Now remember, that is the answer. That's how we do that problem. But what we're doing here is we are finding the y value on that function that we're getting really close to as x gets really close to negative 2. So on this problem, it works fine with fractions as well. We still have to do the same thing. So I go 2 squared plus 1 over 3 times 2 squared minus 2 times 2 plus 5. On the top, I get 5. On the bottom, 2 squared is 2 times 3 is 12, minus 4 plus 5 is 13. So in this case, that limit is 5/13. One thing with a fraction is you always need to put the x value in first before you go factoring, and we'll see what I mean by that in just a second. On this one, I take 1 minus 2 times 4, which gives me the square root of negative 7, just like in every other problem. If we try to take the square root of a negative number, we just say that the limit does not exist. We cannot do that, so we try, we fail, does not exist on number 3. Number 4, I take 5, I plug it in, 9 minus 5 squared, that's the 4th root of 16. You can't do that as well, negative 16, excuse me. So that one also does not exist. We cannot find that one because it's just, again, it's a 4th root of a negative number. You can never have an even root and have the number be negative. It just doesn't work that way. On this one, I take 5, I plug it in, 2 times 5 squared plus 3. That is 53 on the top. On the bottom, 5 times 5 squared gives you 125 plus 7 more is 132. And the reason why that one's on there is, I mean, that's just a strange number. You don't see that very often. But that happens from time to time. You get weird answers, and they're the right answers. Number 6, I take negative 4 and I plug it in. I get negative 4 to the 4th plus negative 4 to the 3rd. Negative 4 to the 4th is 256. Negative 4 to the 3rd is negative 64 over 12 times negative 4 to the 3rd, which is, I'll just put it as negative 64. So 12 times negative 64 plus 128. And quite honestly, I'm not even sure what that number is because I can figure it out real fast. So 256 minus 64 divided by negative 12 times 64 plus 128 gives me negative 3/10 or negative 0.3 is what the calculator spits out on that one, okay? Now on number 7, when we take 0 and we plug it in, I get the sine of 0 divided by 4 times 0, which is 0 over 0. Now that's the indeterminate form, and when you get the indeterminate form, what you have to do is try and factor if you can, and if it doesn't factor, then what we do is we look at a graph. So you need to go and put this function with the x's in it into y1 on your calculator, and then you let it graph, okay? When you do that, for the most part, it just kind of goes like this or on the x-axis, and then right around the origin, it hops up just a little tiny bit. It doesn't hop up very much, but it's pretty easy to see that that hops up to a y value of 1/2. So that's what that limit is. So if you can't factor when we get the indeterminate form, what we do instead is we just look at a graph of the function to try and figure out what it is. On number 8, I just take 0, I plug it in, e to the 0 times the sine of 0. E to the 0 is 1, the sine of 0 is 0, so 1 times 0 is 0. No indeterminate form here. A little bit different because we've got an exponential function, but it still works the same way. This one, I've got the ln of e times e squared minus 4e plus 1. Now, there is an e button on your calculator. On the TI-84s, it's the second button, and then the divide sign will give you e. Whoops. So let me type that in second. Divides. Not second. Yeah, second divide sign. So I'm just typing it in right now. Minus 4 plus 1. That gives us, in this case, and I have had a couple of questions about this, you can get a negative limit. There's nothing wrong with that. In this class as well, and we haven't discussed this very much, but in this class we always round to 4 or 3 decimal places. No matter what, it's always 3 decimal places. So in this case, I get negative 2.484. So that gets us through the first section where we have to find the limit. That's probably the section that'll take the longest, to be honest, just because you actually have to type stuff in and figure stuff out. Oh, I guess these ones take a little while too. Average rate of change, remember, what we're doing on average rate of change is we are finding the slope that exists between 2 different points. These are both the x values of those points. So I get 3 times 1 squared minus 2, which gives me 1. So I've got one point that is 1, 1, and then f of 4, I go 3 times 4 squared minus 2. 4 squared is 16 times 3 is 48 minus 2 is 46. So I've got the point 446. When I want to find average rate of change, that's just the slope between those 2 points. So that's just y2 minus y1 over x2 minus x1. Oops, that's 4 minus 1. So 45 divided by 3 gives me 15. That is the slope of the secant line that connects these 2 points here together. On this one, I do the same thing. I know it's a little bit different because we've got 0 and we got pi halves. But if I take 0 and I plug that in, g of 0 in this case gives me 2 times the cosine of 0, which is 2. Then I go g times g of pi halves. I take pi halves, I plug it in. 2 times the cosine of pi halves. Cosine of pi halves is 0, so 2 times 0 is 0. So there's my 2 points right there. So I just go 2 minus 0 over pi halves minus 0. And you can leave your answer like that. It gives you a decimal 1 point something if you type it into your calculator. You can do that if you want. You don't have to. That's number 11. Now on number 12, I've got my x values here, but there's nowhere to plug them in. That means that the y value is the same the entire time. So no matter what the x value is, the y value in this case is always 0. So I get 0 minus 0 over 900 minus 0. That's 0 over 900, which is just 0. That's my answer. That's my slope of my tangent line. Hopefully that makes sense. On this graph, when we have this graph, I want to determine whether or not a limit exists. Now remember, a limit exists if from both sides, when we approach that particular x value, we are getting closer and closer to the same y value. So as x approaches d, you'll notice as I get closer and closer from both sides, that limit exists because it's the same y value on both sides. So we would say yes to that one. A one-sided limit just means from that side, am I getting closer to a number? And the answer to that is yes. From the other side, am I getting closer to a number? The open circle doesn't matter, so I say yes to that one too. But overall, because those one-sided limits are different, that means the overall limit as x approaches c does not exist. That is a no on that one. Hopefully, again, that makes sense with the one-sided limits. On this one, determine whether the function f is continuous at the given point. So I go to x equals negative 4. Well, right there at x equals negative 4, I can see that there's something going on. There is a jump, well, I almost spelled that with a y, jump in the graph, because the y value suddenly changed from positive 3 to negative 2. At x equals negative 1, so I go to negative 1 right there, I can see that there is no jump, there's no hole in the graph, so there is no type of discontinuity there. Then at x equals 4, because there's a hole in the graph, we have a removable discontinuity. Okay? On this function, if we don't have a graph of the function, the easiest way to tell where a function is not continuous is just by setting the bottom equal to 0. In this case, when I do that, I get that x equals 4 and x equals negative 1. So I would say that the function is not continuous at those two x values, and it's continuous everywhere else. Okay? Now, on this one, okay, I've got a different graph. I need to determine each of these things. The limit as x approaches, and that's supposed to be 1 from the negative side. That turns out to be 1.5, because that's what y value I'm getting really close to from this side. On the left-hand side, or on the positive side, I can see the y value is 0, because that's what we're getting closer to. And then k of 1 is simply asking what is the y value when we actually get there. So where's the closed-in circle? That is 0. Now number 25, which is the next question, asks us to use limits to describe that exact same situation. The only reason why that is the case is because 1.5 does not equal 0. Not all of these are equal to each other. If all three of those numbers were equal to each other, then we would say that the function is continuous. So that was the answer to 25. On 26, what we do to find out again where a function is continuous is we set the bottom equal to 0. So at x equals positive 1 and x equals negative 1, we know that this function is not continuous. Now, from there, we need to say whether or not that's a jump, a removable, or an infinite discontinuity. If those factored forms do not cross out with anything that's on top of the fraction, then we say automatically that those are both infinite discontinuities. Both of them are, because they don't cross out, and so that's where an asymptote will occur instead of a hole in the graph. Number 27, we just have a bunch of jump discontinuities at x equals negative 1, x equals 0, and x equals 1. Because again, the y values jump all of a sudden from one to another. So that's on that one. On this one, again, I factor the bottom. I get x minus 2 times x minus 3. So I know that at x equals 2 and at x equals 3, I have myself a discontinuity. In this case, because x equals 2 is on the top and x minus 2 is on the top and the bottom, at x equals 2, there is a hole in the graph, which means that is a removable discontinuity. For at x equals 3, because that's still on the bottom and didn't cancel with anything, that is an infinite discontinuity. And that's totally fine that we have more than one type on any type of function that we are looking at. Nothing wrong with that. Lastly, number 29, you'll notice that there are no x's on the bottom of this fraction. There is a fraction and it has x's on top, but there are no x's on the bottom. Since that's the case, there are no x's on the bottom, then we can say that this is continuous everywhere. There is nowhere that we have a discontinuity because there's nowhere that the bottom is equal to 0 to create the issues that we've had before. So that is all of the problems that we have looked at when it comes to this particular review. If you have any other questions or you need some help, please get a hold of me before we take the test.